So let's see how we take a look at this graphically. Now here I'm representing an endothermic reaction because the well, let me back up. We're going to define the parts of an energy diagram, okay? And I'm using an endothermic reaction to illustrate the parts of an energy diagram. So here we have a graph and we have our line here. We've got a line. Let's take a look at each part of the graph. So on the y-axis, we're looking at potential energy, or delta H. On the x-axis, we're looking at the reaction progress, going forward in the reaction over time. We have two lines here. We have our potential energy of our reactants versus the potential energy of our products. Now, moving from our products to this top peak that we have here is going to be what we call the activation energy. So this is called the activation energy, and that peak here is called the transition state. It's a hypothetical state in which we assume that all of the atoms rearrange themselves in this reaction in the right position in order for the reaction to occur. So the energy that is required to go from the energy from the potential energy from our reactants to this transition state is called the activation energy. It is the minimum amount of energy that must be supplied to break the bonds in our reactants. So it's a minimum amount of energy required to break all the bonds in the reactants. So we can say that this is the sum of the bond dissociation energy of our reactants. Okay? Now, the difference between the potential energy of our reactants and the potential energy of our products is delta H. And like I said, the difference between the potential energy of our products and the potential energy of our reactants is our delta H. So given a graph that has numbers on it, you can do what? You can, number one, you can tell the activation energy. Number two, you can give the potential energy of our products and the reactants. And you can also determine the delta H for the entire reaction just by subtracting these two values, okay? So the activation energy would be this line, all right? The difference between, so the activation energy is, let's say the potential energy of our reactants. Nope, I wrote that backwards. It would be the potential energy of our transition state minus the potential energy of our reactants. Okay, that's the activation energy. So let's take a look at the difference between an exothermic and an endothermic reaction. For an exothermic reaction, notice that our reactants have a higher potential energy than our products, and the energy that is released, or delta H, is the difference between our products and our reactants. The activation energy is going to be the difference between our reactants and our transition state. Okay? Whereas looking at an energy diagram for our endothermic reaction, notice that our activation energy goes all the way from our reactants all the way up to our transition state, and the energy that is absorbed by our reaction is is found here between our reactants and products. Now, let's take a look at this activation energy. So hold on, I want to ask this. What type of reaction would have a higher activation energy? An endothermic reaction or an exothermic reaction? Endothermic reactions always are going to have higher activation energies than exothermic reactions because you have to put so much energy to break those bonds, get them to the transition state, and for the reaction to occur. So, before we move on to our next topic, let's do a couple of practice problems. Let's take a look at this reaction. Notice that I have written here our delta H. Uh-oh. Our delta H. Notice here that our delta H is negative. It's not, I'm not writing it in the reaction, but it says that it's negative. So based on what you've learned so far, is this reaction endothermic or exothermic? Yes, it is going to be exothermic. Now, if I was going to write this energy in the chemical equation, would I write it as a product or a reactant? Well, for this situation, delta H, or the energy released or gained, um, since it's a product, delta H would be, I just gave you the answer, huh? Since it's negative and it's exothermic, we know that this energy is being released. So the energy, say the energy is a product, and we would write our plus this amount of kilocalories in our chemical reaction. Let's now do these practice problems together. How much heat in kilocalories and kilojoules is released during the combustion of 0.35 moles of methane? And also, we're going to look at how much heat is released during the combustion of 7.50 grams of methane. So we want to know how much heat is released during the combustion of 0.35 moles. And then we're going to look at how much energy is released when we burn 7.50 grams. Now, wait. How do we do this again? Remember, this is stoichiometry, and we have to use our balanced chemical equation to help us solve this problem. And remember, it's always going to be, we're thinking about grams of A to moles of A, moles of B to grams of B. Or for A, let's see, for number one, we're going to go from grams of A. No, not grams of A. We're going to go from moles of A to energy. We're going straight from moles to energy, and it's based on our balanced equation. For the next one, we're going from grams of A, moles of A to energy. Now, going from moles to energy, that is going to be our delta H. Here, getting from grams of A to moles of A, that is going to be our molar mass. All right, so let's do these problems. Move you back over here. All right, for the first problem, what are we given? Our given is that we have 0.35 moles of methane, and what we need is the amount of energy that is released per mole of the energy that's released per 0.35 moles of methane. So we're going from moles to energy, and that moles to energy is delta H. So what is that energy? So if you go back a slide, we have the value that's there. And so let's work this problem out. So always starting with what you're given, I have 0.35 moles of methane, and I'm going to use the conversion of our delta H. Remember, it was minus 213 kilocalories per what? Mole of methane. So I end up with minus 74.55 kilocalories. Now, could I have used the kilojoules value? Absolutely. Now, why did I keep the negative? Well, I kept the negative because why? That lets me know that this energy is being released. Oh yeah. Okay. But there is no such thing as negative energy, so the value that you would report based on your number of sig figs is going to be the positive value of 75 kilocalories. All right, let's do the second problem. What we were, oh, sorry. So let's take a look at this value in kilojoules. We can take that value from kilocalories, our minus 74.55. Notice I didn't round off here because I want to have a more precise answer. I could have just plugged in the kilocalories here, but we can convert from kilocalories to kilojoules. And our conversion is 4.184 kilojoules per 1 kilocalorie. And we get minus 311.9, but we're going to report that as 310 kilojoules because I need two significant figures, and we cannot give energy as negative values in our answer. There's no such thing as negative energy. Remember, the negative tells us that energy is released. Okay, let's move on to the next problem. Given that we have 7.5 grams of methane, I need to know the energy. So how did we say this problem was moving? I'm going from grams of A to moles of A to the energy. So starting with what we were given, 7.5 grams of methane times our molar mass. What's going to go on top? The moles of the grams. The moles are going to go on top for methane, and methane molar mass is 16.0 grams per mole. Now, our grams are going to cancel out, but now we need to convert from moles to energy. We're going to use our conversion with delta H, and this time I'm going to start with the kilojoules. So I have minus 891 kilojoules per 1 mole of methane in our reaction. Everything cancels out, and we get minus 417.7, but we're going to convert that to positive because remember, we cannot report energy as negative values. So our answer is 420 kilojoules.